and thanks for joining us today. Our introduction to Preparative Supercritical Fluid Chromatography. I'm Josh Lovell, one of the application specialists here at Teledyne ISCO. And today, luckily, we're joined by my colleague, Todd Anderson. He is a global chromatography specialist. And Todd has a strong, diverse resume in purifications and specifically with supercritical fluid chromatography. Todd started his career doing process chromatography for Chiral Technologies in 1994. And he installed his first Prep SFC instrument in the late 90s and worked at Merck Pharmaceuticals running a high throughput mass directed purification lab and chiral lab utilizing SFC. And then finally, before joining our team at Teledyne ISCO, Todd spent several years working with various preparative HPLC and SFC equipment manufacturers. And we're lucky to have Todd on our team today. So the outline for today's discussion is we're going to break down the introduction to Preparative SFC into a few different areas. And first, we're going to describe why are we considering Prep SFC as an alternative technique to some other purification methods. We're going to discuss what is a supercritical fluid, what is supercritical chromatography, and some of the theory and background behind that. We're going to compare Prep SFC to more commonly used techniques such as Prep HPLC and see where the similarities and differences lie. We'll also discuss some examples of common uses of Prep SFC in certain application areas, and then also where it's emerging in other application areas as a more popular technique. And we're going to discuss kind of the difference in the Prep SFC workflow from the traditional Prep HPLC workflow. And then finally, we're going to look at some of the obstacles that that have hindered the broadened use of Prep SFC in different areas. So why do we want to choose Prep SFC? Well, so some of the benefits from Prep SFC is that it's a comprehensive chromatography. It's very commonly used in chiral purifications already, and it's seeing expanded use in achiral purifications. It also offers, as an alternative orthogonal technique to reverse phase HPLC methods, where maybe we get purification from one impurity using our Prep HPLC method, and then we get a different selectivity and a different type of purification for that final polishing using SFC. The other thing is there's an alternative selectivity because there's so many different stationary phase options that are used in Prep SFC, and it offers us a wider solvent polarity range for our compounds in a single run, where we're a little bit more limited with the solvents that we use in preparative HPLC. The other thing that it offers is higher efficiency because of some of the characteristics of supercritical fluids. It allows us to increase the throughput, and we're able to run at 3 to 4 times faster run times than Prep HPLC. Additionally, it eliminates, one of the liquid solvents at the end as a supercritical CO2 that's used during the purification. Once that reaches atmospheric pressure, that is going to evaporate off and is eliminated very, very easily. This results in faster processing time due to less solvent and more concentrated fractions. And then we also don't have water to remove from the fractions. So that's going to result in energy savings in the processing steps. It's also a greener technique. We've reduced solvent consumption during the run. And then we've also reduced the solvent waste generated and that needs to be processed at the end of the day. And also the energy needed to remove the solvents. The nice thing about supercritical fluid chromatography is it reuses carbon dioxide. So it's CO2 neutral technique. The CO2 that's generated from other industrial processes or from the atmosphere is captured, and then we can reuse that and give that CO2 second life. And finally, Preparative SFC offers numerous safety enhancements. So compared to other techniques like normal phase chromatography, we're able to eliminate some hazardous organic solvents. They've been replaced with CO2. Compared to reverse phase, we're able to eliminate the use of acetonitrile. And the nice thing about CO2 is that it's non-toxic. And when we use appropriate co-solvents, it's safe for use with food and pharmaceutical products. So we've discussed why we're even considering preparative SFC as a technique, and there's some great advantages to it. But I think a lot of people wonder, how are we able to, how does SFC work? What is a supercritical fluid? What is supercritical fluid chromatography, and what are the properties behind it that allow us to take advantage of the higher throughput and be able to use it as a purification technique? So, what is a supercritical fluid? That's the first question. And so if we look at a phase diagram here, we have, our three states of matter that we can see and touch and breathe, and solid, liquid, and gas form there. And you'll notice in the upper region there's a point, and that's called the critical point. And above that region is where a supercritical fluid exists. And it's essentially a liquid or a gas that's above its critical point. At this point, the density, viscosity, and diffusion coefficient change continuously from a liquid-like to gas-like values, but there's no actual phase change. And so this is kind of a unique process. And what we see here, if we look at the critical temperatures and pressures for some different compounds and that are used in different areas, we can see that there's some unique properties to carbon dioxide that are very advantageous for using it as a purification technique. And if we look at the critical, the temperature at the critical point and the pressure at the critical point, those are both easily achievable without much energy input. So for the case of preparative SFC, we're going to be referencing carbon dioxide as the kind of the unique and exclusive solvent of choice at the moment. And so throughout the presentation, we're going to be referring to CO2 as the base solvent there. No, so the previous diagram was looking just at a pure single compound in its phase diagram, right? Now, chromatography is usually going to be a mixture of binary or even a ternary mixture of fluids. And so how does that impact supercritical fluid mixture? And so to really, it's pretty complex to be able to come up with exact values for this, but to visualize this, we have this graph on the side, and what we need to do is, this is for an example of a miscible mixture of CO2 and methanol. One of the advantages of supercritical carbon dioxide is that it's miscible with methanol throughout the entire range, unlike some nonpolar solvents like hexane. But if we add a third axis to our phase diagram, we can see that this third axis represents the concentration of methanol with the CO2. And you can see how that impacts the supercritical region. And so basically the gray region and below there is where within that shape there is where we're going to have a liquid vapor transition, and it's not supercritical. And then above that region is where we're supercritical, and basically percent composition is going to impact that. And you see kind of a shape to that rather than a linearity to it. You can see the difference there between the critical temperatures and pressures of carbon dioxide and methanol. Methanol has a very high temperature critical point, but the pressures are actually very similar. So that makes it a little bit easier to help achieve supercritical fluid state with the mixture. Now we've talked about supercritical fluids and kind of the theoretical landscape, but to me, I want to be able to visualize it. What does that really mean for us? So as we look at the pictures here from left to right, we can see that if we increase pressure and temperature, we're going to move towards a distinct liquid and gas phase where we have two layers coexisting on the left. And as we increase the pressure and temperature, we reach a subcritical state, but kind of a two layers there still that are visible. But once we get to the supercritical point where we've reached critical pressure and the critical temperature point, we can see that there's only one layer there essentially. So at that point, it's a miscible, or a solvent that we can use for chromatography where we don't have partitioning and things like that. And in the supercritical state, we can take advantage of that. So if we specifically look at the properties of supercritical fluids that contribute to the chromatography and the changes that we observe by going and using supercritical chromatography, we can specifically look at the diffusivity, the density, and the viscosity as we compare it to gases and liquids. And we're going to notice kind of some mixed properties here for supercritical fluids that really kind of enhance its behavior and make it a very useful solvent for chromatography. And so when we look at the diffusivity, it's a very high diffusivity that's more gas-like than a liquid. Okay, so it's kind of in between a gas and a liquid there, and several orders of magnitude higher than what a liquid would be. But it also has a liquid-like density, though, so it's more like a liquid in that sense, and that contributes to the solvating power of the supercritical fluid. And then it also has a really low viscosity, and that's where it's also more gas-like. So we have 10 to 100 times lower viscosity than liquids. And the really important thing, if you think about Prep HPLC, is what limits our flow rates really. It's our pressures on the columns that we generate, right? And by changing to a much less viscous solvent mixture, now we're able to kind of push that flow rate and not have the back pressure and damage to the column that we, or in our stationary phases, that would be possible with other techniques. We already mentioned the high solvating strength, contributing by the density there. In addition to just kind of the nature of carbon dioxide, also has some unique weak Lewis acid effects. There's zero surface tension in the supercritical fluid, so that helps once again with using that in a flow system. And we can tune the solvent strength by changing the modifier strength or adding a additive to the mixture. So we can change the how the compounds are eluting down the column by adjusting the solvent strength that way. And then finally, carbon dioxide is great because it's non-toxic, so it's easy to use in the lab and is a great alternative. So moving on to the next section, we're going to compare Prep SFC to Prep HPLC. And there's a lot of people probably who have some experience with Prep HPLC, and we'll kind of use it as a basis to establish what supercritical fluid chromatography is. So what is SFC? It's a chromatography technique using supercritical fluid as a mobile phase. And what we're talking about specifically here is preparative SFC, and we're not talking about flash. So the best comparison is to preparative HPLC. They're going to have similar resolution and kind of similar purity in the end as an outcome. And so you'll see SFC both at analytical and prep scale. And I think one of the reasons that we're seeing more preparative SFC techniques is analytical SFC has taken some great leaps and bounds in the past decade to 15 years, where they've made improvements in the consistency, and it's become a more popular analytical technique. And that makes it easier to transfer methods to preparative purification. One of the other things we talk about is, or that we kind of mentioned before, was how the modifier percent can impact the chromatography or the supercritical state, but so can the pressure and the temperature that we have set for the method. So if we increase the pressure, change the temperature, that can also impact our retention in our chromatography. But ultimately, it's the high diffusivity and the density paired with the low viscosity that results in higher flow rates with low pressures for our separations. And this is what results in runtimes that are about 3 times shorter than what we see with Prep HPLC. If we look on the right, we have a Van Diepter equation of comparing the linear velocity and the plate count for HPLC versus SFC. And you'll notice here that for the SFC curve, it's a lot flatter at the bottom there. And so what that means is that it expands the range where we can increase the linear velocity or the flow rate of our purification without losing resolution in our plate count. And so we can have good efficiency at a higher flow rate, and then we can take advantage of that in our methods. The other way to visualize this also is you can see the Venn Diepter plot here with the particle size. So as we decrease particle size, we kind of get a similar effect that flattens out that curve. This would be applicable to HPLC and SFC here, but it's a good visualization as how increasing the efficiency of the run via flow rate allows us to work in different flow rate regions. The other way to look at this, to think about preparative SFC, is that it's a normal phase technique using supercritical CO2 as the base solvent or our weak solvent. Supercritical CO2 has a similar polarity to heptane, and it's suitable for purification of nonpolar compounds. As we add organic modifiers to the mobile phase and our supercritical mixture, this increases the polarity and it can assist in eluting more polar compounds, just like that we see in normal phase elution in flash or even in preparative normal phase HPLC. Now, some of the differences is kind of in the terminology that we see in a lot of the SFC literature versus what we see with the preparative HPLC literature. And the solvent is an SFC term, and that's going to be our carbon dioxide is going to be our base solvent. Our A solvent and LC terms are our weak solvent. Commonly, you're going to see modifier used, which is sometimes used in LC terms to refer to the additive. But the modifier in the context of SFC is in reference to the co-solvent. You'll see co-solvent and modifier used interchangeably. And this represents our strong solvent or our B solvent in LC terms. And then finally, when we have a modifier, such as an acid-base modifier that we're using to improve our peak shape or our chromatography, we refer to that as an additive in SFC. So just wanted to square away some terms that we may see throughout and how they may be different. So what's different from HPLC? Carbon dioxide. This is it acts almost like a super solvent, has great solvating strength. The miscibility of CO2 with polar solvents really expands the polarity range. And I know Todd will elaborate a little bit on that later and how that can increase kind of the application areas that we can use it. And this also brings its set of own considerations for choosing to use Prep SFC. So, we need to have tanks of CO2 available. You can do this in several different ways. You could have a bulk CO2 supply that's piped in from outside the building. You could, run a system off of a CO2 tank with a liquid dip tube where you're pulling liquid CO2 off the bottom of the tank. You can use low pressure dewars with a booster pump. There's a lot of different ways to get CO2, but it is a consideration you take a look into so that you can have your infrastructure set up. The other thing you need to consider is, where does the gas go when you're done, right? So you can't let that go into the atmosphere of the lab, for risk of asphyxiation from CO2. So you need to be able to have that inside of a hood or some sort of enclosure that is able to then exhaust away the CO2 from the run. CO2 is also really cold, so there's a concern about frostbite with cold fittings and things like that. So something to be aware of when you start, if you were to happen to have a leak of some sort. The other nice thing about CO2 is environmentally friendly alternative to organic solvents and is safe for use with food and pharmaceutical products. So when we compare Prep SFC to Prep HPLC, what do we see in regards to performance? And what we'll find is that we see similar stationary phase loading amounts for Prep SFC to reverse phase. You could probably take advantage of the solvating power of the CO2 a little bit to increase that loading capacity. But in regards to the stationary phase, maxing out the capacity of your stationary phase, they're going to be very similar. The biggest advantage is that we're going to be able to run at 3 to 4 times faster flow rate. And so that's going to result in increasing our throughput and our efficiency and getting more done in less time. The other big thing is that we're using less organic solvent, right? So we could reduce the amount of organic solvent by up to 8 to 9 times, depending on what the conditions of the chromatography are. And so for reducing the amount of organic solvent, that means it's less solvent we have to rotevap later. And then specifically compared to reverse phases, we've removed water from the equation, right? So we don't need to then freeze dry or do other techniques to remove water from our sample that are pretty high in energy consumption. So there's up to 7 times lower energy consumption for solvent removal when comparing it to reverse phase techniques. When we compare it to a normal phase preparative HPLC, you're going to have, a higher purity. It's going to go you'll be able to run it faster because of the lower viscosity. Maybe able to use smaller particle size because of that. Significant reduction in the amount of organic solvent that you're using, and that's going to result in less workup time as we have more concentrated fractions, meaning less solvent. So the next slide here, we're going to discuss some SFC mobile phase modifiers and additives that you commonly see. And as we mentioned before, supercritical carbon dioxide has a similar polarity to hydrocarbons like hexane, heptane, cyclohexane. And common co-solvents that are used are going to be methanol and ethanol. Those are pretty common. A lot of the selectivity difference that you'll see is going to be found in stationary phases, and we'll discuss that in a few slides later. Some other solvents that you could see used would be isopropyl alcohol, acetonitrile, methylene chloride, and chloroform, as those can kind of offer some different solubility characteristics for some compounds and change the selectivity also. But traditionally, those are going to be because of solubility. The nice thing about being able to use CO2 and methanol, like we've discussed, is this wide range of polarity. So we can run from 0 to 70% methanol without miscibility issues. Water is sometimes used as an additive for SFC, so it's not common. It's not used as a solvent, and normally this is used up to 5% mixed in the organic, so like 5% water in your methanol, and that's added in either isocratically or as a gradient just in the methanol. These are commonly going to be used along with other additives such as acetic acid, ammonium acetate, TFA, methylamine, or triethylamine. And the idea is hopefully that it'll improve peak shape or also maybe enable chromatographic elution there. So we get better separation with it. In many cases, you decide to use this acidic basic modifier for acidic, basic, and amphoteric compounds that don't elute or are eluted with very poor peak shape with binary solvent mixtures of CO2 and methanol and ethanol. And we use the additive in this case to help tighten those peaks up down the column. Other additives that are commonly used include acetic acid, ammonium acetate, TFA, methylamine, and triethylamine. The additives hopefully are used to improve peak shape or even enable chromatographic elution down the column. It's nice that they can be used to help kind of force the compound into a favored state as it travels down, so that you don't get the acid-base equilibrium is pushed one way in the chromatography there. You see this a lot used with acidic, basic, and amphoteric compounds and to improve their peak shape. The other thing is that CO2 is kind of nice, and it allows us to maybe get away from using additives sometimes, and because of the weak acidic nature of it compared to some other base solvents that we use with other techniques. So it allows us to kind of get away from the additives also. At this point, I'm going to transition to Todd here. He's going to discuss Prep SFC applications and workflows.
Thanks for passing it over to me, Josh. Welcome again, everyone. Sorry I didn't come in and introduce myself, but Josh did a great job of doing that earlier. So I'm going to go ahead and just sort of look into some of the examples of Prep SFC applications that we're going to be trying to develop here in the near future, and some that they're being used in the fields already. The first one we're going to look at is kind of a chirality primer, for those of you who may not be familiar with chiral separations, but that's pretty much where the history of chiral SFC has been over the past couple decades. It's been a very strong tool for preparative chiral purifications because of some of the things that you can do to it. So I'm just going to put up a couple pieces of information here about what chirality is. So basically, it's just a left and right of a chemical structure. So you can actually have a dex or a levo, and based on the structure of it, is going to basically determine the enantiomer that you're going to be trying to separate. For that, I'm going to use an example and why it matters. Many pharmaceutical products are produced as single enantiomers. One of the compounds that happens to be very common in the United States, I know it may be not as common in some of the other parts of the world, but here in the US, I use it quite frequently, is Aleve. And the beginnings of Aleve is now, even though it's an OTC, started out as a pharmaceutical compound. And here's the compound structure. So if we look at that, we wonder, how did they separate that? How did they get that purified as a single enantiomer? Well, originally, they developed the drug Anaprox to treat arthritis. Unfortunately, during the testing, it was determined that only one of the enantiomers was truly effective, and the other enantiomer actually caused some risks of liver poisoning and some other derogatory side effects that they wanted to get rid of. So they decided that they needed to purify this, and they couldn't get it to separate based on recrystallization or preferential synthesis. So they decided to go the chiral separation route. What they were able to do is actually pack the compound into a column, run different compounds through it, and then the compound that stuck the best is the one that they actually use to do the purifications. So why would we want to use SFC for chiral purifications? Well, first off, you're going to be able to use higher solubility for chiral SFC due to the fact that we can use methanol as opposed to ethanol or IPA. The CO2 that we're going to be using with it is also going to aid in our solubility. So we're not going to have to worry about the hexanes crashing out many of our compounds. The other thing is we can actually achieve faster run times with a minimal dry down time because of the CO2 being gaseous when it comes back out of the column. You don't have to worry about the compound sitting there in a large volume of vessels. We used to rotovap down up to 50 liters of solvent at a shot, trying to do bulk purifications. By the time you get done, there's a chance that you might actually have heated up the compound enough that it has re-racemized or maybe decomposed. So with the CO2, we're pretty much staying at a room temperature environment, evaporating off most of the CO2 just through expansion. And then the minimal amount of methanol that you have left is usually pretty easy to evaporate off. So we also get a reduced need for additives, as Josh mentioned. We've been very fortunate in certain cases to not have to add in an iron pairing agent. So one of the techniques, if you have like an amino and an acid group on the same molecule, is you would have to put in a DEA or TEA, as well as a TFA or other acidic component. If we can get rid of one or the other, then it makes the purification a much more streamlined process where you don't have to worry about desalting the compound after you finish your purification. The CO2 actually will add some acidic properties when you're combining it with methanol, and we can actually sometimes get rid of the acid altogether. Again, with all of those other, the last two points, gives us a reduced chance of racemization because it's a quicker dry down, it's a quicker reconstitution of your compound that you can go ahead and pass along to wherever it's going next. So here are some of the common chiral SFC column stationary phases. As I had mentioned earlier, the naproxen sodium was a compound specific column, but it turned out that came to be the Welco one column, and you can actually use it for multiple compounds. It became a little bit more of a universal chiral column. But these are some of the other chiral stationary phases that are out there that are getting mimicked. Some of these are off patent. So some of these are chiral technologies proprietary. Some of them are just generic compounds now that people are actually making their own columns from them. But as you can see, there's a plethora of compounds out there that they use for chiral stationary phases. It leads us to understand a little bit more why SFC is a useful tool for this, because it's easier to switch the columns back and forth. As you'll see, there is no real specific one column for SFC. So we slide into this slide, and what we can actually do is traditional achiral possibilities are now being expanded into SFC as well. So you don't have to look just at the normal phase nature of SFC to do your purifications. People are now starting to transition the regular reverse phase and Hillick type compounds into SFC as well. So with that, what does that mean about columns? Do you use a C18? Do you use something different? Well, that's where we get into something a little bit more tricky. So what we see here is a large selection of columns that are being used for what we would traditionally say reverse phase type compounds. We're now using things like a silica, a diol, cyano, ethylpyridine. You can see that there's a large variety of compounds that they are putting on to the siloxyl group to go ahead and make new types of stationary phases, which leads us back to what do you use? Well, it's not going to traditionally be a C18 anymore. We don't have one of those yet for SFC. In another webinar we're going to be doing later this quarter, we'll be going into some more in-depth study of the different column and the stationary phase effects of chromatography. But it's a great toolbox for changing your chromatography. So we can actually broaden the spectrum of compounds that we can actually separate on one instrument. You don't have to have a flash system. You don't have to have a normal phase system. You don't have to have a reverse phase system. We can actually do a lot of those different things just by changing out our column and our solvents for selectivity. So what applications are we actually seeing SFC being used in currently? Pretty much anywhere that chromatography is being used. We're using it in natural products, essential oils, fish oils, and there's, I'm sure, some other natural products out there that people are familiar with as well. Pharmaceuticals, which is pretty much the bulk of what I'm familiar with. But we are stepping into some of the things like biologics, steroids and peptides, foods and flavors, where things have a very low boiling point, and traditional chromatography drying down can sometimes cause them to lose most of the yield. With the SFC, we're finding out ways that we can actually purify even some of those that are extremely volatile. And we also get into fine chemicals and agrochemicals, which have a lot of crossover to them. But this is today, and we're going to be moving towards tomorrow, where we're actually going to be trying to find new application areas for the SFC market. Now we're going to slide into SFC workflows and how the traditional SFC instruments have been designed and how we actually envision them being used in the future. So one of the two different Prep SFC workflows, the bulk purification is what most people have been doing in the past. The collection has been done with a collection valve. You come out of the instrument and you have one of maybe 4 to 12 bottles, and you basically collect into a vessel of some sort to rapidly evaporate your compound, evaporate off the solvent from your compound. It has limited fractions. There's not a lot of flexibility to it, but it is great for stacked injections or for repetitive injections, bulk injections, and that's why we kind of prefer to call it bulk purification. You're basically repetitively putting one material in there and collecting one fraction or 2 or 3 fractions out on the back end. The other possibility, which has only come really into play within the past couple years, we did some of this work back in the 90s, but trying to collect into separate vessels can be very complicated. How do you keep all the liquid into one tube, not get aerosolization of your compound? Overpressuring vessels if you're using capped vessels. Recently, one of our competitors came up with an idea of how to do this, and they've put a device on the top of the fraction collector and started collecting liquid samples into vials. And we came up with a different way of, as you can see in the background, we have a system that is actually doing that right now. But what we would want to do is multiple samples for purification. So if you have 2 or 3 different compounds and you want to put them into maybe 7, 8, 9, 10, 12 different tubes, we can actually just continually collect fractions like your traditional HPLC or Prep HPLC would be doing. We don't have to be limited by the number of valves you have on the back of the instrument. We can actually go and collect into multiple tubes for multiple compounds. We can also look at seeing this becoming more popular with mass spec. So there's a couple vendors out there now that are using mass spec to tie to their SFC instruments so that they can do multiple injections, and then we can limit maybe to 2 or 3 tubes per injection. But that means if you can load up 6, 7, 8, 9, 10 samples in a row, we can handle that in the industry for collecting that many samples, and we can actually collect fractions across the spectrum of compounds. Let's see, the next is, what is stacked injections and what can it be? So this is just a simple chromatogram. You'll notice that there's an isocratic elution in the background at about 20%. We get 2 compounds coming off and possibly maybe a little bit of an impurity in between. And that works out pretty fine for us. But the samples have to have minimal to no impurities elsewhere. As you can see, this compound does have a little bit of an impurity between the 2. So what you would do is typically run a bulk scale purification for most of your compound. And then we would basically get the compounds that were unable to be resolved in a different mode by using a different column. As we go through the isocratic elution, we will try and separate these 2 compounds fractionally. Even if we don't have a full resolution, we could in theory have like the interstitial space collected into a 3rd tube and then just repeat that over and over again. But the best operation is where we can actually have the single and secondary peaks, first and secondary peaks, I should say, fully resolved, so that we can just keep repetitively putting those compounds right back into the same vessels. So we minimize the number of fraction locations. What does that look like when we actually stack them though? We would have to look into the runtime of the method or the actual elution. So in this case, we have a runtime of maybe 2.5 to 3 minutes. And we're going to look at the cycle time. So the cycle time is actually that time between the first beginning of peak in the back of the secondary or last peak that we want to collect. That's going to be our cycle time. And then once we couple that information all together, we can have a nice stacked sequence of compounds that are coming through the column. Usually this is going to be used in chiral chromatography. As you can see in this case, it's 2 of the same compounds with a little impurity in the middle. But we're starting to look at this for other applications as well, maybe like proteins or peptides, things where you might have a small impurity that you just can't quite get fully resolved. So we can stack these injections for a very small amount of a time window and maximize the amount of compound we have on the column at any one given time, which will increase our throughput and increase our total yields. So as you can see, we have a comparison of a single cycle time might be a 3-minute single run. But then once we do the full entire injection and we multiply that out by the amount of time savings, you can see how the throughput has drastically improved by being able to do our stacked injections. So traditionally 3 single runs, 7 injections would be 20 minutes. In this case, we can put the same amount of throughput and we're down to 9.5 minutes. So just think of what that would wind up being if we were to stack that over the course of several hours. You can drastically and exponentially increase your throughput. What they aren't. One of the things that you cannot do with stacked injections is have some form of a gradient or a clean out process in the middle of the stacking. The reason we can't do that is pretty apparent. If you have a non-isocratic elution, some peaks are going to be getting swept through the column way too early as you make those injections at certain time points throughout the run. So in this particular chromatogram, for instance, if we tried to make an injection somewhere around 4 or 4.5 minutes, that first peak is already going to be moving through the column, and it could potentially elute almost with that void elution and cover up that secondary peak. So we cannot do gradient profiles with stacked injections. Why would we want to do stacked injections? They can greatly increase your throughput. As I mentioned before, we can increase your return of investment for your capital. We can reduce the amount of solvent lost, reduce the amount of solvent being utilized. Collecting fractions in bulk like this, we can actually create a lot more larger pools of fractions. We can also do normal phase, which leads to quicker dry down times. Originally, we worked with this slide for doing normal phase chiral separations, but we're seeing this being used almost on every system out there. The idea is to try and maybe have the system doing stacked injections on SFC as well. But that allows us to do quicker dry down times. And it greatly reduces the overall solvent consumption. So we're going green and everybody likes to go green. So yeah, we're going to try and reduce a lot of the wear and tear on the system, the solvent, but basically it all boils down to being able to load more compound in a shorter amount of time. We can also remove, this is a secondary use of it, but we can also do close eluting impurities and to get them out of the way to get higher purities as we move forward. And with that, we're going to move into obstacles to broaden use of Prep SFC. And I'm going to transition this back to Josh, and he's going to go ahead and take us to the end of the presentation. Thank you, and I'll talk to you in a little bit.
Thanks, Todd, for the great talk regarding the applications and the workflows that we use in SFC and breaking that down for us based on your experience. Greatly appreciated. So finally, as Todd said, I'm going to kind of bring this home, and we're going to discuss some obstacles that have inhibited the use of Prep SFC from being used more broadly. And so one of the limitations for Prep SFC, just historically, is that it's required large system footprints. So, there's a need for chillers, back pressure regulators, elaborate collection systems so they can get rid of the CO2 in a controlled and safe way. And this is all in addition to traditional Prep HPLC components, such as pumps, detectors, ovens, things like that. And so what that's resulted in is systems in the market that have very large space requirements and infrastructure needs. And, the cost of lab space is very high. It's valuable real estate. And many systems are, extremely large bench or skid systems currently, and they require a significant commitment to be able to use and the space available. The other limitation here is a lack of versatility and limited applications. Todd mentioned that, chiral separations has really been kind of the niche role for Prep SFC and highly needed. But achiral purification really hasn't taken off as much as Prep SFC probably could contribute to it. And one of the reasons for this is that many systems are dedicated to bulk collection. So, there's not really many open bed fractionation options out there that allow you to do multi-sample operation or maybe to to clean up, we want to collect multiple fractions from a sample. You know, a lot of times those systems have required custom modifications or an alternate configuration, limiting the versatility from switching back and forth between bulk and multi-sample operation. So that requires more of an upfront expense because you have to have 2 dedicated systems for it. Additionally, it's complicated systems. I mean, the properties and dynamic nature of supercritical CO2 depends on a lot of variables. So as we get changing temperature and pressure from our CO2 supply, you know, we really require robust pumping solutions. You need accurate flow control and automated back pressure regulation to adjust as the dynamics of the CO2 change so that we can have stability in our chromatography. Another major consideration, you know, we discussed large system footprint and infrastructure, but CO2 supply is something that has to be considered. You know, can you run the system off a single, how many tanks of CO2 do you need to be able to do that? Are you running off of a low pressure supply with a booster pump? Are you fortunate enough to be able to have a bulk CO2 supply solution already piped into your lab? And this is all considerations that can kind of go in and add to the cost of being able to implement Prep SFC. You know, the other thing is you're going to require proper chilling and exhaust venting requirements to make sure that you're using it in a safe laboratory space. Some other limitations, you know, there's been a lot of, you know, since there's not a lot of systems out there, the software out there is typically kind of burdensome because there's not much competition to make it a more user-friendly experience. You know, there's complexities to the software interfaces because there's intricate hardware needs, and there's typically an external PC interface that takes up space, and there's the potential for dropped communication because there's so many independent system components going on, and there's a lot of kind of custom, you know, piecemealed SFC systems out there that really require expert knowledge to be able to handle the software communication. The other thing is there's a reliance on Windows, and you know, anytime there's a software upgrade for Windows, you're going to worry: is my software going to be fine with it, or I'm going to have problems and need to wait for the next software update to be able to meet the IT security requirements that the lab that's constantly changing in the lab. There's been another issue is there's been poor sample recovery options. So, you know, Prep SFC has gotten to the point where we've been able to get good sample recovery for bulk collection, but you know, open bed collection is still kind of a new frontier, and there's not many options out there because of the need to separate CO2 gas from the liquid safely before collection. You know, this has been a limiting factor, and it leads to method limitations, maybe sample loss or poor recovery, or a combination of the three. And there's just not many open bed fraction collection options to choose from. Another limitation that a lot of customers have is that there's system reliability issues, and then there's a lot of service requirements for it, and maybe difficulty getting service depending on where you're at. The complexities and custom nature of some of these systems results in a difficult to maintain system. And with a limited number of systems, there's not many service experts out there, and they require specialized training, and they're probably busy at other sites also. So they're difficult to you know, take advantage of their availability. I think the final thing is really Prep SFC to this point has been really an expert users only kind of niche category. You really had to be an expert to use it. The additional parameters for SFC compared to HPLC requires expert knowledge or a friendly user interface for non-experts. But cumbersome software interfaces have a high learning curve. So that's really limited the implementation of Prep SFC kind of into the mainstream. So to kind of summarize kind of what we discussed today, and we really want to highlight the benefits of Prep SFC here because it's something to consider. There's some great advantages to it as opposed to other techniques, and can offer some you know, significant benefit to changing towards. So, to review, we discussed kind of the comprehensive chromatography offered by Prep SFC, how you can use it for achiral or chiral purifications, how it's an orthogonal technique to reverse phase HPLC. So we could go in there and use that as a polishing step if we weren't able to get clean purification from our HPLC step. The alternative selectivity from the various stationary phase options and the wide solvent polarity range. Todd went into detail, kind of previewing some column stationary phase choices and that are out there to choose from. I think the biggest thing is the higher efficiency. I mean, time is valuable in the lab, and to be able to run it 3 to 4 times faster than Prep HPLC and not have to worry about and not having to worry about processing as much fraction solvent, right? So removing the solvent and not having to worry about freeze drying or anything like that, that cuts down on the development time, and you're going to see higher turnover from or turnaround time, between your purification and your clean product. And so that's always important this day and age in our industry, being able to react more quickly to change and to move faster through the pipeline. Another major incentive in a lot of industry is how can we be more friendly to the environment, going green, right? And so this is a great opportunity here for us to be able to transition some of our high solvent use purifications towards a Prep SFC technique that reduces solvent consumption. It reduces your solvent waste generated, and it requires less energy to remove solvent. So it's kind of a home run in regards to minimizing the cost and environmental expense of using all of these solvents. It's a CO2 neutral technique, reusing CO2 generated, captured from other processes or the atmosphere. So we're not generating any new CO2, we're reusing it and giving it a second life. And then finally, the safety enhancements. So being able to use less hazardous lab solvents, less volume of them, that's important. And I think, always a good consideration for the workspace. And then finally, just in the process of food and pharmaceutical products, CO2 is non-toxic, and you can use appropriate co-solvents for effective purifications and have positive results with those. So finally, I want to invite you guys to join us February 2nd. Todd and I are going to be introducing the AccuPrep SFC and discussing Preparative Supercritical Fluid Chromatography made easy. On February 22nd, our colleague Jack Silver is going to be discussing new techniques for Prep SFC method development. And March 8th, Todd's going to be joined by a guest speaker, Matt Prisbacel from PerkinElmer, to discuss choosing a Prep SFC column. If you're doing chiral separations, achiral, what are the options out there? How do you choose the right one? And so that'll be a great talk, and we're lucky to be able to have Matt from PerkinElmer join us in collaborating with that. And then later this year, with dates to be shared later, we're going to have some specific webinars focused on stacked injections, chiral purifications, auto sampler and open bed fraction collection, and kind of the library process and more. So, we look forward to you joining us for those webinars, and we appreciate you guys taking the time today to join us and listen about preparative supercritical fluid chromatography. Feel free to follow us on Facebook, Twitter, LinkedIn, and YouTube, and get updated application notes, updates on that, updated product releases. You go to YouTube, you can find a recording of our past webinars and this webinar. And at this point, we're going to open it up to questions. So we'll go ahead and begin, Todd. So one of the questions was, how can a SFC be used for oligonucleotide purification? And I think we can expand that to peptides also, because I think that's a common theme.
Yeah, I would agree. So one of the things that you wind up running into is the solubility of your compounds and how can you get them onto the column. One of the nice things about SFC for chiral compounds is that typically you run into issues for the traditional normal phase chromatography where you're limited by ethanol or IPA for the traditional columns, and you wind up not getting a really good solubility. So with SFC, you're able to actually load them up into methanol. And so we can load them at higher concentrations, put the methanol in there and actually run that way. The problem with oligos and with peptides, typically you're going to wind up running into a lot more issue with aqueous solubility. You're going to be a little bit less organic soluble and a little bit more aqueous soluble. So that's one of the difficulties and limitations that we typically see with SFC is getting the compound onto the column in the first place. Recently, we've been doing a lot of discussions with some of you actually that I've scrolled through the list while I was not speaking. And some of you have actually brought up these to us in the discussions we've had coming and leading up to these webinars. One of the things that we're looking at is trying to look at different solvents as co-solvents that might actually help us in changing the dynamic that people see about SFC. Traditionally, we would not typically use water in the mobile phase at all. But in this case, we are looking at some different things that might actually help to change some of those issues. So as we learn more, we're going to continue to do webinars and maybe add some more of this information back to you so that we can all help you with your processes as well.
Right. I think one of the benefits of, I think we're seeing an increase in kind of the percentage of modifier that people are using in the SFC or even in enhanced fluidic liquid chromatography. But you're seeing more polar compounds being able to be purified and kind of pushing the fringes, and you're seeing new development in the labs as they're able to apply these techniques to a broader base of solvents. One of the other questions here was, what do we mean by open bed fraction collection? And I can take this one, but basically, if you think about your traditional, reverse phase HPLC separation, you got your fraction collector, and we're going into test tubes, basically enabling users to do that with SFC, which has been difficult in the past because of the gas expansion as we go from the supercritical state to the atmospheric pressure at the outlet there. So that's been problematic. So open bed fraction collection is really a newer capability for SFC that hasn't been used as frequently, and you're seeing more people move towards achiral purifications and replacing some of the reverse phase purifications with SFC to take advantage of this. Let's see here. Let me pull up the other questions here, Tom.
So I'm actually answering the one right there from Larry. So I sent that over to Larry. But the question was, can we get a link of the upcoming webinars that we're going to be having in the future? And we will definitely add those to the webinars post-recording link that Sharon's going to send out. So we'll make sure that we get that information to you as well. If not, you can always go onto our website and they're linked there as well. You want to go ahead, Rob? Or yeah, Josh.
I know you're used to chatting to Rob all the time, so.
I know. Of course, he didn't need to show up. So
yeah, we'll have to talk to him about that. How about what different kinds of detectors can be used with Prep SFC? I think that's a good question.
Yeah, it's a great question. So typically what we're traditionally using is UV chromophore detector. So our detector specifically is a 200 to 400 nanometer range. So we can actually do UV and do compare and contrast analysis of the compounds that we're seeing. What we're looking into next, and what some other customers have actually already implemented, is SFC MS. So they're actually implementing the MS into the SFC systems. We're looking into ELSD, and we're also looking into some other possible chiral detectors, but that's down the road. Right now, we're just going to start with the traditional UV chromophore deuterium type detectors. Can you think of anything else that we're going to be, or anybody else is using?
No, No, I think that you covered ELSD, mass spec, and then I mean other external detectors have been used there. So it
Hey,
traditionally
Josh,
hasn't. Yep.
we got another question pop up about how can we actually what was the question? How do you actually perform open tube collection? Is the bed pressurized? No. So there's been a lot of attempts to try and do open bed collection, if you will. Back in the 90s, the first couple systems that we tried to do this with, we basically capped the vials, pierced the septa with the collection needle, pressurized the vessel, and the caps popped off. That didn't work. So we had to go ahead and put vents in it. As you can imagine, the vent was okay, but you would still get a lot of vapor and potential solubilized or aerosolized compounds getting pushed out of the vent tube. It just was not a very good way to do it. What we do is we've actually, instead of just opening directly to the atmosphere, we have a chamber that is actually a gas liquid separator. There's two different ways to do that. You can put the gas liquid separator directly on the head of the fraction collector, where the aerosol goes up into the atmosphere, and it allows the methanol that's in the system to drop slowly down through this depressurization device. They used to have cyclone separators, all different other kinds of things. What we do is we have a separator that's actually on the side of the instrument that before it ever even leaves the system, we've already depressurized the CO2, and the stream that we have coming out of the backside of the instrument and through the collection valves is nothing but, for the most part, I'd say 90 to 95% methanol. So we do get some expansion of CO2 as we come out, but it's not too bad. We just basically take a drop tube down inside of the test tube and have a little bit of a curvature to it, so that we actually are coating the sidewalls of the vessel, the tubes, whatever you're using, the bottles. So we can actually have what we consider an open bed collection. Hopefully that answers your question. Did that sound about right, Josh?
Yeah, no, I think that's a good answer there. I think one of the earlier questions was, looking at a mixture, a supercritical mixture, fluid mixture, in the change in the essentially the kind of combined critical point and critical pressure. How do you know that you're at the supercritical state? And then that's a good question. I think it's also a complex one that I'll try and hit on here, but so that's changing as we change the percent modifier throughout a gradient, that critical temperature pressure point for the binary mixture, or as you add other additives, it'll change too. But there's also a field of chromatography, enhanced fluidity liquid chromatography, that's similar to SFC, and it's essentially kind of in the subcritical state where you get a lot of the benefits of SFC, but you're in the subcritical state. And there's some really good papers out there showing that there are, the kind of the same advantages: lower viscosity, high solvation, and you get a lot of the same benefits, even not necessarily being above the supercritical state. So it's really a complex question, especially as you start changing the percent B there. So I would kind of advise you to look at the enhanced fluidity liquid chromatography for more information there. And there's some good articles comparing that to supercritical fluid chromatography and the benefits there. I think we got another question here is, could you substitute flash chromatography with Prep SFC? And can you inject multiple times to kind of achieve the same scale as our torrent, for example? And so Todd discussed kind of the wide range of compounds that we can purify using Prep SFC. So it definitely overlaps with normal phase separations. That we have the CO2, which is very similar polarity as heptane, but we're able to use it with methanol up to 100% potentially, with the miscibility there. So you kind of expand the polar range of that. You could replace flash chromatography with a prep separation. Normally, when we get to the prep separation step, it's usually going to be kind of a polishing step. Chiral separations, we've kind of got a clean mixture just so you get all the gunk off first, so you can maximize the loading at this scale. You can do multiple injections. We talked about stacked injections. Todd did a good example of that, how they can stack injections in an isocratic method for that, and that really does optimize the throughput. I don't know if you'd be able to get to your torrent scale there. It would depend on the process and how optimized it was. You could replace some purifications with that, but you'd be limited because of the size of the columns and things like that at this scale. See, Todd, I got a couple other questions here. What is, do you use anything outside of binary gradients with your co-solvents mixing with the supercritical CO2 in your experience?
That's a great question. I have not personally used anything much more than methanol, to be honest with you. My experience has mostly been traditional CO2, methanol purifications, maybe adding in acetonitrile or pre-mixing some solvents. What we're seeing a lot more of in the research being done now is that people are actually asking to do some blending and starting to ask about, can we actually do, how can I say it? Solvent selection switched to actual solvent proportioning. And we are looking into that because our instruments can do that. There's no problem with it. Nobody ever really saw the benefit to it though, until just recently. We're starting to see a lot more research out there where people are actually co-blending solvents to change some of the affinity and some of the elution properties of the purification. So yeah, we're going to definitely be looking into many different solvents. As I mentioned earlier, water is one of the new solvents that we're starting to hear a lot of. People just putting in a little bit there into the system will help us a little bit more with that polarity issue that we're running into. In the past, I was always told and chastised, you ever put water on the system, you might kill your column. But that doesn't seem to be as much of a problem anymore, especially with the different columns that we're starting to utilize for SFC purifications. So yeah, anything, we're looking into maybe using some DCM, water, obviously methanol acetonitrile. Josh, have you tried anything in-house?
We have done, we've done, some testing with DCM and ethyl acetate. Nothing inspiring as far as applications yet. So just using them.
I mean, as far as the functionality of them. Yeah.
Yes. So, yeah, definitely.
Yep. So we can actually start looking and doing more things with it. And we're more than willing to hear feedback from you guys to see what you want us to do. We're here to help you guys out. So it makes sense for us to listen to you.
I got three final questions. One, what's the largest column size you can use on the system? So the flow rate range of the system, we'll talk about this more in the next webinar, but we'd be talking about 2 and 3 centimeter diameter columns for this scale of system. So it's going to give you similar loadings to the what you would see on your Prep HPLC columns also. I think your loading per mass of stationary phase is going to be very similar because you have functionalized silica normally with these separations, so it'll be similar loadings. And then Todd, if you want to elaborate just on what kind of purity levels of CO2 are needed for to be able to do preparative SFC.
Oh, sure.
We'll wrap up with that one.
Well, me personally, you want your CO2 to be as pure as you can. But to be honest with you, if it's food grade and we have a dip tube CO2 doer, that should be perfectly fine. Most of the people are concerned with some of the costs of ultra pure CO2. I think I'm actually traveling abroad in the UK right now, and some of the issues over here are safety and purity and all that other stuff. But your local soda dispenser's got CO2 in it. We can pressurize that CO2 and use that CO2, and that should be relatively safe for the compounds that you're putting on there. And there's usually not too much of an impurity that's going to cause a problem with your chromatography.
Fantastic. I think that is all the open questions there. I want to thank everybody for joining us today. just a reminder, our next webinar, the Preparative SFC Made Easy with the AccuPrep SFC will be February 8th, just as a correction there from earlier. Todd, thanks for joining me today and sharing your expertise with us, and hope you guys have a good rest of your day.
Thanks, Josh. Thank you, everyone. Take care.